Okay, so I'm going to talk about COPASI, which is the other major application that we're presenting or describing in the course. So COPASI is a simulator mostly for temporal systems, so it does not do the spatial part. So the major difference between COPASI and virtual cell is that virtual cell can simulate heterogeneous spatial simulation, whereas in COPASI, each compartment that is simulated is a well-stirred environment. So inside each compartment, all the molecules are distributed uniformly in that compartment. Now, of course, you can have several compartments, and so you can have some kind of heterogeneous distributions by having defining different compartments. So it could be a nucleus and a cytoplasm and a Golgi, for example. But within each of them, all the concentrations are uniform. So there's no diffusion, essentially. Apart from that, COPASI can simulate the dynamics using three different approaches. The first one is differential equations, very much like virtual cell did. It can also do stochastic simulation, also like virtual cell, but then it also has a third method, which is not present in virtual cell, which are stochastic differential equations. So these are differential equations that have stochastic terms, also known as noise terms, that can be arbitrary. They could be the regular ones from physical chemistry, but they could actually be any possible shape of noise. It also allows you to have discrete events. And the other major important part, which Les already had mentioned, is that COPASI can calculate steady states automatically. So it has criteria, and I'll talk quite a bit about that later on. You can also characterize them for stability, do parameter scans, do some stoichiometric analysis. I will describe most of these in a little bit of detail later on, and parameter estimation. Parameter estimation is basically when you have a model and you're trying to estimate the values of some parameters, and you use data from experiments for that. And so you could think of it as data fitting, model fitting. There will also be a presentation dedicated to parameter estimation tomorrow, so I will not say too much about it today, but bear in mind that this is one of the most used features of COPASI, and certainly we have a specific dedicated presentation tomorrow. Optimization, those optimization algorithms are used for parameter estimation, but they can also be used in any arbitrary way, which means in a model, you can try to find the maximum or minimum of any variable or function of variables in the model. It has characterizes models using sensitivity analysis, and metabolic control analysis is a special kind of sensitivity analysis. And it allows us to do some other more or less well-known, less popular methods for characterizing the dynamics of a system, such as cross-sections, Lyapunov exponents, timescale analysis. This we will only discuss if somebody is really interested. We don't have any specific presentation, but if you're interested in these methods, then certainly throughout the course, I'll be happy to talk about them. There's a number of ways in which COPASI presents data, as in two-dimensional plots and surface plots. And you can produce reports that you can define in different flexible ways. You can also show some network diagrams. And apart from being a graphical user interface, as you can see here from 3 different windows captured, one in Windows and macOS and Linux, so it runs on all of those. And it's written in C++. However, it is also possible to write code for COPASI. So if you want to write scripts, you could do that in Python and R. Those are particularly better catered for languages. It's possible with others, but those two are mainly the ones we're promoting. And I'll also talk a little bit about this. And in my other presentation tomorrow, more of a research presentation, I will also describe particularly the Python interface. Okay. So I think this is kind of the generic overview of the capabilities. One of the things is that COPASI has rather widespread adoption. It's used all around the world, as you can see from that distribution map over there, in many different areas of biochemistry and chemistry. Chemistry is actually probably about 50% of the use of COPASI by people in chemistry that has nothing to do with biology. Also some biological chemistry, of course. And these here are the journals where we find papers that use COPASI. As you can see, there's a prevalence of computational biology journals and also chemical journals there. And about more than 100 papers a year on average since 2016. So about in the last 10 years, we've been having about 100 papers using COPASI every year. There is a web page, this one here, the URL. If you go to that web page, which I can could show later on, that lists all the papers that we identify that have published some model using COPASI. That's also a useful resource for you to find papers perhaps in the same area that you're working on and maybe read them and find out inspiration on how they're using the software. When you use COPASI, we would like you to cite this paper, which is basically the main description of the software, which is now almost 20 years old by now. It's the major one. There's a more recent one in 2017 that we described it again, a more recent version. It's more dedicated to biotechnology, but that's also fine to cite that one as well. Now, in a book quite a number of years ago, we also published step-by-step instructions on how to use the main functions of COPASI. It's in this book, and I've also put the article, a copy of this, a PDF, is in the Google Drive that Michael Blinov will, I think he's already posted the link on the chat, but he will also send you that by email, I'm sure. So over there, you can download this paper if you want, as well as my presentation. I have not uploaded it yet, but after I finish, I will put it there as well in the Google Drive. So other documentation that is available is on our website mostly. There's a user manual, there's a forum, there's a bug tracking system, and there's some technical documentation. The manual goes into some details of the methods, not an enormous detail, but you get some details about the methodologies and the various algorithms and what things are mentioned and some references, etc. In the forum, you can ask questions. This is actually run through Google Groups. You can ask questions, and then ourselves in our team or other users sometimes will hopefully answer your questions that you have. Okay, so to get a little bit more into detail, the simulation methods that we have available in COPASI, as I mentioned, there's three major ones. ODEs, that's mostly the most used one. And the differential equations in COPASI are built directly from the reaction kinetics. So you actually don't normally write the differential equations explicitly as a user. As Laszlo mentioned earlier, we target our users to be mostly biologists interested in doing simulation, not so much mathematicians. So the software will try to build all the mathematics itself. Of course, you have to enter the reaction kinetics because the software does not know what it is, even though there is a menu of many different functions available, and you can also enter your own specific functions if you have kinetics that are not in the list. Of course, you can add arbitrary ODEs, it's possible. So that would be, for example, things such as electrochemistry or osmotic pressure, things of that kind that are not reaction kinetics, not chemical kinetics, then those would have to be added as arbitrary ODEs. And then another important factor, although it's not very widely used, but it is possible, and it's one of the few software that allows you to do this out of the box, which is the compartment volumes in COPASI can also be variables. You can define differential equations that govern how the size of a compartment changes. And it could change, for example, with the size of the molecules, or it could just be changing as a function of time. And everything else gets calculated properly. So even though we have not seen many models that are published that use this feature, it is available and it's possible. So I like to always highlight that. Then the second most used approach is perhaps the stochastic kinetics. That's based on the Gillespie's algorithm. So it assumes, as Laszlo described, that the reactions are probabilistic, and it uses probability distributions and a Monte Carlo type simulation that essentially generates a stochastic trajectory. And then if you run many of those, if you repeat it and run many of those stochastic trajectories, you can then describe the distribution of the trajectories. You can find out what kind of behavior and how much noisy the behavior is using that. And then the final one, which is the stochastic differential equations, this is a little bit like the normal or ordinary differential equations, except in this case, you add a noise term for each reaction. Each reaction can have a noise term, and that noise goes according to any distribution that you may wish to add in there, and then the system gets, so then it will be stochastic, a little bit like the Gillespie approach, but it is using a different formalism. And the reason why the two exist is that while the Gillespie approach is more physically realistic, the stochastic, it does not allow you to have large numbers of molecules, whereas the stochastic differential equation approach can be used in systems that have large volumes. It's not as restricted as the Gillespie approach. And then all of these types of models can have specific algebraic assignments. That is, you can specifically write an algebraic function for something, and you can add discrete events that depend on either the time or some condition that you define for the model. Okay, so when you create a model with COPASI, this is the underlying mathematics. These are the differential equations, which are, as you know, functions or algebraic sums of the rates of the reaction. So positive for reactions that produce a certain species and negative for reactions that take the species away. And of course, if a reaction is involved in two species, it is going to appear positive in one case, and here V2 is positive, and in another case being negative. So here for A, V2 is negative. So in this case, that same equation here, which is the enzyme kinetic expression for that rate of that reaction, appears in two different differential equations. Now, this is all built automatically by the software internally. So what types of analysis COPASI can do? When the most basic one is actually stoichiometric analysis. These are properties of your system that only depend on the reactions, not on how fast those reactions happen. So it is totally independent of the kinetics, and these properties are properties that always exist in any state of the system. So for example, the most basic one is mass conservation relations. So if you had added these small networks as examples to your model, let's say the first one, then COPASI is able to find out that these conditions hold true. So for the first system here, you could see that M and MA, every time one reacts, forms the other, and vice versa. So that means that their total is constant. So this is what we call a conserved moiety or a mass conservation relation. The second one, you will find out a similar case where M goes to MH and MH always goes back to M, so that you have a very similar expression here, M plus MH equals to the total. But you have another one which you may or may not be able to identify by eye, but obviously COPASI does automatically, which is MH minus B is also a constant. There is a total amount that is fixed in the difference between these two. And that reason is because every time you consume M, you produce B, and every time you consume B, you produce M again. Actually, I think I made a mistake. It's MH minus B is equal to a constant. And then the other approach, the other stoichiometric analysis. Okay, was there a question?
It's actually either one. It's not well defined.
Yeah, the value for the total would be different if you choose one or the other. Okay, sorry about that. It was actually right as well. Okay, the other approach the other analysis that is only based on the stoichiometry, that is the reaction network, is the so-called elementary flux modes, and those COPASI basically, these are calculates those automatically, and the elementary flux modes are like specific small subpathways that you could isolate out of your network, and that those subpathways could function autonomously. That is, they would function allowing either a steady state or an oscillatory system, but they would not accumulate or deplete the system of the mass. And of course, in this example here, you see the underlying network underneath with the arrows, and these two shaded areas are two different elementary modes. They could be pathways working on their own. So you could reconstruct only this portion, and that's included in the observable system. Okay. These are the properties that are not dependent on the kinetics. So this you could calculate even without adding kinetic functions. Everything else following now requires that we choose kinetic functions, and they are the normal ones. So the most basic simulations that COPASI can do are time course simulations, trajectories, and steady state. So I'm going to describe those two. First, the time course simulations. So this is the interface of COPASI for defining time course. Essentially, all time courses look the same. You have a certain duration for the time course, and you can define how many intervals in that time course you're going to sample. That's not the integrator is not governed by this. It's governed internally by what step size it needs to use. These are the number of time points that you're going to output. So internally, the step size can be smaller or larger than that. But that's really when you're instructing the software to output data at 2000 intervals. So that, of course, for 60 seconds, 2000 intervals, that means that you get an interval size of 0.03 second. And you can either type the number of intervals, or you can type the size, and the other number gets calculated automatically. And then the other important thing here is to pick the algorithm that you're going to use. And so in this case, deterministic means it's an ODE approach. So, so the software is going to carry out the simulation based on ODEs, and you would get something like that. This model example is a calcium model that has oscillations, so-called bursting oscillations here in one of the calcium species. And then, however, you can also run this stochastically, and if the conditions are right, and I'm not going to mention them here, but essentially you have to have, very briefly, you have to have all the reactions, the forward and the reverse reactions have to be entered separately, and you cannot have too many molecules in the system that is calculated by COPASI. If those two things are true, you could just change the, you could just pick one of these stochastic algorithms from the menu, and then you calculate the system in using the Gillespie approach. So that's how easy this is. Going from ODEs to stochastic is basically changing a menu entry. And then this is the kind of trajectory that you would get. Now, as I mentioned, you need to have a small number of particles, and you have to have the forward and reverse reactions all separate. And if you don't, COPASI could separate them in the tools menu. There is a way of doing that. But most of the times it's possible to do automatically. Sometimes you have to do it manually. The other major simulation approach COPASI has is the steady state. And I'm not going to spend a little bit of time about talking about steady state, because this is, as we mentioned before, this is one of the types of calculations that COPASI can do and virtual cell cannot do automatically. I mean, you can do it as Les mentioned, but does not have an automatic detection method. So what is the steady state? So this definition of a steady state is the state of a system when the concentrations of all the species in that system have become constant. So if you have a steady state, if your system has a steady state, after a while, concentrations do no longer change, and that is what we call a steady state. And so the steady state definition is that really the rate of change of each species is equal to 0. That's the definition here. And if you think about it, if you say that all of these equations have to be equal to 0, then you no longer need to solve a system of differential equations. You can actually solve a system of algebraic equations. Here they are. They happen to be nonlinear because each of these terms, v1, v2, v3, v4, is actually a nonlinear function. So this is not simply solving systems of linear equations, but it's solving systems of algebraic nonlinear equations. And if there is a solution, if that is possible, because that's not always not necessarily the case, but most cases you do get a solution. And if there one exists, then that solution will give you a set of concentrations, which I'm denoting here with a small case a and a small case b for species A and species B, which are the concentrations in the steady state. And that's what we call a steady state solution. Of course, you can also calculate what are the rates of reaction, the V's, at the steady state, and that's also part of the steady state solution. And just as in passage, to remind people of this, it is possible to have more than one steady state when you have more than one variable in your system, which is most of the times you have models with more than one variable. So even with one variable, you can have more than one steady state. And so if there is more than one, then it depends on your initial conditions, which one you're going to reach. Now, there is a very special steady state when you have a closed system, or it could happen also in an open system, but in general, these happen in closed systems. There's a very special steady state, which has a very special condition. So in the steady state, we said that the V's are all equal to 0. So this V1 minus V2 is equal to 0. So we say V1 is equal to V2. And then from the second equation, you could say that V2 is equal to V3 plus V4. And for a steady state, you just need to hold this condition. So V1 and V2 could be 16, for example, and that would be a steady state. However, if V1 is equal to V2 is equal to V3 is equal to V4, and they're all 0, this is still a steady state. It's kind of a virtual case because there's no net reactions happening anymore. And in fact, that steady state in chemistry, we call equilibrium, chemical equilibrium. So we distinguish between the two, and COPASI will identify an equilibrium as such. If it says steady state, then it decided that the fluxes are larger than 0. These V's are larger than 0. And the two are important because in equilibrium, basically nothing is happening. It's really not a dynamical system anymore. Whereas in a normal steady state with finite rates of reaction, then that is a system that even though nothing appears to be happening, there are fluxes that are converting things that just happen to happen at the same rate. I see a question in the chat. I will try to address it later on if that's okay. If it's if it's important to answer it now, maybe one of my colleagues can try to address it, but I think I'll get to it at the end. Okay. So how do we solve for a steady state? So I mentioned already that you could just solve the algebraic equations, and that's one possible approach. That's this number 2. Number 1 is what Laszlo already mentioned, which is if you calculate a trajectory and your n time is large enough, that is, if you calculate a trajectory for long enough, then your system will have reached a steady state. And so in COPASI, we use these two criteria to try and find a steady state in an automated way. And I'm going to explain that in a moment. It's also possible to find unstable steady states by doing a trick, which is going backwards in time. So if we go forward and the system is unstable, everything will diverge. But if you go backwards, the things that diverged will converge. So just to illustrate that, you may have seen a movie of a piece of glass being broken, but the movie is passed backwards. So if you see the movie backwards, you see the pieces of glass coming up together in forming a bottle. That's exactly what we're doing. We're running the simulation backwards so we can find something that was no longer stable, the glass that got broken, but we find that unstable steady state by integrating backwards. So COPASI can also do this and find some unstable steady states. So the solution by time course essentially does the following. It starts at a time course and it asks the question, are these things changing or not? Now, this question, are these species changing or not, is a little tricky. It's less obvious than it appears, or it has a lot more complications than you may think at first sight. Like in the first plot here, you could say that everything has already relaxed. It doesn't look like anything is changing. Maybe this one here is still slightly changing. However, if you plot this in logarithmic space, you see that there are a few more that are also changing quite a bit here. And so this might not be good enough for a steady state. The question, of course, becomes how small should the change be that you can already consider it to be zero? And that is expressed in two criteria that we formulate in COPASI, a distance criterion and a rate criterion. The distance criterion asks the question, what is the difference between the current concentration and the concentration I just calculated a little bit before? And is that number smaller than an epsilon? This epsilon is the number that you decide that below that anything is zero, right? So it's a small number and anything below that number is zero. So the distance criterion looks at one time point minus the previous. There is a second criterion, which is the rate criterion, which looks at how small is the estimated differential equation, the dx dt. And if that, which should be zero, remember, right? If that dx dt is smaller than certain epsilon, then we can consider that this is a steady state because the changes are small enough. And that's called the rate criterion. So in COPASI, we actually can use one or the other, but the default is in fact to use the two. So we call a steady state when both the distance and the rate criterion are smaller than epsilon, whatever the user sets as the epsilon. Then how to solve for algebraic equations, we have here the Newton method, and unfortunately this would have an animation, but I forgot that the PDF, which has what I'm showing you here, this doesn't work out. But this is a root finding algorithm, the Newton-Raphson method. By the way, if you look this up in Wikipedia, that's actually, in fact, I have a typo on Raphson there. This will have an animation. This came from Wikipedia, the image made by this author, and you will find an example of how you find this point by starting arbitrarily here. You get a tangent, you hit this point, and then, of course, that's your current solution. Then you take that there gets this point, then you look at this one, then that will get that point, and then eventually you hit the minimum. And that's basically the function that is used in this Newton method. And that's the these are the differential equations, and this is what we call the Jacobian of the differential equations, which is a matrix of the partial derivatives of all the differential equations. And so this requires a matrix inversion. This is a vector divided by a matrix, which is a vector multiplied by the inverse of a matrix. So you don't have to know about these details. I'm just highlighting what algorithm is used. This is very fast when it works. Unfortunately, it's not guaranteed to work. If you start too far from the solution, you may never actually get to the solution. And so this one is not guaranteed, and that's why COPASI uses two algorithms. So COPASI has this hybrid strategy, which is it tries the Newton method first, and if it checks the criteria, remember the rate and the distance criteria, if they are actually passing, that is, if the solution that the Newton method found is already a steady state, then we stop there and the whole thing is solved. Most often it isn't. So in that case, COPASI will run a small short time course, the 0.1 unit of time, and then calculates the criteria at the end of that. Again, if it finds them, it stops. If it doesn't, then it tries the Newton method. With the outcome of this simulation becomes the guess for the Newton method. Oops. And then it tries again. And if that doesn't work, then it's going to run that time course multiplied by 10 times. So it was 0.1. Now it's going to go for 1 second and tries again. And if that doesn't work, it goes back to do Newton method and then goes back integrating longer. And it does this 10 times. So eventually it stops. If it went all the way to 10 to the 10 units of time and it didn't find a steady state, then it just quits. Maybe there would be one if it tried another time, but at some stage you have to stop. And here is an example of what COPASI, in a specific case, what it actually did. So you could see the distance and rate criterion here failed. So it does integration, they still fail. Tries Newton method again, they still fail. Then does integration. As you can see, they're now already small. Here as well, and that doesn't work. Newton method is still small, they're getting smaller. And then finally here, it fits, they both reach the criterion, which was 10 to the minus 9. Actually, 10 to the minus 8, I think, in this case. So they're both below 10 to the minus 8, in which case it hit this solution is good. It does one more step just to get the data even more refined. So that's an example of how COPASI calculates steady states. And then once you calculate a steady state, it gives you an outcome, which is, as I mentioned, the steady state solution, which in this case would be the concentrations of the species. These are the concentrations in the steady state. And then these are the rates, which you can see are all very close to 0, which is why it is a steady state solution. And then you can also choose another tab. You see the fluxes of the reaction. So in this case, here are the fluxes. And in this condition, these fluxes are large enough. They're not below the threshold. So this is considered an actual steady state, not an equilibrium. Okay, so these are the two main operations in COPASI: time courses and steady states. Everything else works on top of one of the two. For steady states, we can also ask the question whether they're stable or unstable. COPASI will tell you that. I don't have a lot of time to go into the details. If you want to know about the methodology to decide whether they're stable or unstable, we can discuss that offline later on. But the main thing in modeling, the reason why you make a model, and in the previous presentation from Oni, it was very clear that this is always the case. You always ask the question, how do the parameters affect the state of the system? And this question appears in different forms. It's not formulated like this all the time, but all the time when you're modeling, you're trying to find out what is the relationship between the parameters and the outcome on the system. How the parameters affect the state of the system, that is the dynamics of the system. And even though the question is this, it comes in different formats. For example, these 3 examples here are all asking the same thing. How do the parameters affect the state? For example, you could be doing drug design and ask the question, which parameters have the highest effect on the desired outcome? Let's say you want to decrease concentration of certain protein. So what parameters are going to achieve you that outcome? What kind of inhibitors can you add to do this? And that will tell you what your drug should look like. Or you're studying a little bit more theoretical aspects of the biological system, and you ask the question, what properties of this model are more fragile and which properties are more robust? Those two things have effects on the system. The properties that are fragile, towards which the system is fragile, are probably things that make this model sensitive to the environment. The properties for which it is robust are actually things that can change a lot in the environment for which the biological system is not affected. And both of these are important, and both of them are asking the same question. How do the parameters affect the system? In the fragile case, they affect the system very strongly. In the robust case, they affect the system almost nothing, very, very weakly. And then if you're just doing experiments, you also ask the question, which parameters do I really need to have very accurate estimates, and which ones can I just have a very coarse estimate? And whichever is the answer is going to affect how much effort and money you're going to spend on experiments. So this question is also one where modeling could help. If you have a model of your experimental system, that could be one reason why the model is useful. Now, all of these questions have methods in COPASI and virtual cell for which that you can use to try and answer these questions. So, for example, in sensitivity analysis, you actually quantify how much a parameter affects a variable. And that is kind of a linearization. So that tells you, that gives you a metric that is only valid for more or less close to the current state of the system. So if it is a very large change, the sensitivity analysis is not useful. It is useful to tell you what are small changes, but it's easy to calculate and gives you a spectrum, quickly a spectrum of which parameters are the more strong effectors of some certain variable. The other approach is parameter scanning, and that something that Laszlo already mentioned as well in virtual cell. This is one of the most used methodologies in COPASI and virtual cell, which you change a parameter and you see the outcome on the system. And in fact, you can change more than one. You could change 2 or 3 parameters and of course produce a 2 or 3 dimensional or 4-dimensional plot with the outcomes and find out how the parameters affect the system. You could also sample them according to some distribution, like out of a normal distribution or a uniform distribution or something like that, and try to determine the output distribution of the variables if the parameters were affected by random changes. The other approach which COPASI has is optimization, and I do think that optimization was one part of the question here. The optimization algorithm allows you to find minima or maxima of a certain function. So if you define a function that has the answer to your question, optimization algorithm will find the combination of parameter values that could achieve that optimally. And that again answers the question, how do the parameters affect the system? Except that in optimization, you kind of put the question upside down. You ask, how can my system be like this? And then the optimization algorithm will find you the best possible way that that model could satisfy what you wanted. So rather than asking which one affects the most, you change the system to a condition that you would like it to be in, and then you ask, how can I put it here by changing my parameters, essentially. It's called a inverse modeling, in a sense. You kind of do it, you start with how you want the system and you find out what should be the conditions to get there. And then the other analyses, I'm not going to talk about them, but they are also analyses that identify how the parameters change the system, but they do it in terms of either timescales or in frequencies of oscillations. So parameter scanning in COPASI, that's one of the most used. This is an example here. In fact, we have in one case a parameter scan here. You see these many different lines. So there are lines at which for different values of 2 parameters, and you trace out the time courses. And then you can also do the same thing, but change them rather than doing a scan where you say, oh, well, for this parameter, change it between 1 and 10 and steps of 2. Instead, in the bottom approach, which is called sampling, you just say, well, give me 100 random values of this parameter between 1 and 10, according to the uniform distribution, and between 0.5 and 50 to this other second parameter, and then you get the trajectories. Well, you get the results for the different combinations. In this case here, we're looking at steady states, this second plot, and each cross is the different steady state value. So this is the sensitivity analysis. It's asking the question, how much does a parameter affect the variable? So here you would have a parameter. The x-axis is for the parameters. Let's say the Vmax of a certain enzyme. And if that changes, how much that affects a variable, in this case, the flux of the pathway, the steady state flux of the pathway. And so the sensitivity coefficient is going to be the tangent at which point you ask the question. So here it depends whether you ask the question for an enzyme that has a Vmax of 0.1, you get a certain answer, which tells you that the system, that Vmax affects the flux quite considerably. However, if you are in this condition where the Vmax is already 10, then you ask that question, it tells you that, well, that Vmax doesn't control the system much. So this sensitivity analysis, the important part here is that these coefficients are dependent on the state that you ask the question in. So they're state dependent, context dependent, but there are also properties of the system. They're not properties of the specific reactions. They're properties of the whole system. Okay, there's another question there about MCA, and I'll try to get to that at the end. If you get infinities, you probably have a very small flux, and so you're probably in equilibrium, I would think. But I'll try to answer this at the end. Okay, and then in optimization, which I mentioned, this would be the front end for optimization. You define the problem, which is you've defined some expression of your model, some factor in your model that you want to either maximize or minimize. In this case, we're trying to maximize the flux of alcohol consumption, in this case, alcohol dehydrogenase reaction. And you tell it, well, I want to maximize this according to, and you pick a few parameters that are allowed to change. Of course, you have to change parameters, otherwise you cannot make the system change. So essentially you ask the question, how can I get the maximum possible flux if I allow these three parameters to change? And you give it some boundaries. So this formulates the problem, which is maximize this flux, given that you're allowed to change these three parameters inside these boundary values. So the question is, what are the values of those parameters that you get the maximum? So to solve that, we have then a menu of different optimization algorithms that you could choose, and you can run one and then run the other if you didn't get a good enough question with one. Again, the reason why we have several is that they're not guaranteed to converge or find the global minimum. So we have many that can be used. And finally, parameter estimation, which is really an optimization problem as well. Here, we don't define a minimum. The minimum is defined by the experimental data. So you have to enter experimental data, and then you have to link each of the things that were measured in that experimental data to, you have to link them to properties of the model, that is to variables in your model. And once you make that association, you then say, well, I want to estimate these parameters such that, change these parameters such that my model behaves as close as possible to this experimental data. And that is really an optimization problem. In this case, we're minimizing the distance between the model and the data. And it's a very complicated function. It's not complicated, but it's a function which is a sum of squares of each data point, the difference between the data and the prediction by the model. And so that could be a very large sum. In this case, there would be a term for each one of these data points, and they're all squared and summed, and we minimize that. And then you can also choose all the different algorithms that are available for optimization. You can choose them, and then you run this. Eventually, this is showing here, progress of fit is the size, it's the distance between model and data, and you can see it's going down after a while, and when it stops, the model, in this case, it's the solid line, will behave more or less like the data if your problem has been solved. And as I said, we'll talk more about parameter estimation tomorrow, so maybe the most important questions will come tomorrow. Okay, so I'm getting closer to the end. I'm going to mention that it's also possible to program with COPASI, and this has become more and more popular as we go along. In my research talk, I will give some examples of using Basico, which is the Python package for COPASI. But there is also one called Cork, which is for the R language. And both of these provide a very high-level API for COPASI. So you could be writing a program in R and calling COPASI functions. And that way you can write like a whole workflow in a little program that you can run again and again. So you can basically store the list of what you're doing in a nice order, which is very good for reproducibility. It's an important thing. If you just have the GUI and you press buttons and you do things, you had to remember to describe that in a paper, whereas if you do a workflow, that's kind of like fixed in there. And this also allows you to create complex types of simulations and applications. I will describe some tomorrow. And thus you will see some examples of BASI COPASI package can be used. Both of these in these websites, you will see examples, and Basico has a nice manual, has a lot of examples in the manual, and Cork has a web page that also describes and shows some very basic examples. So these are fairly easy to get into if you know those languages already. And finally, there is a cloud version of COPASI, which we have on our website. We're actually in the process of trying to overhaul this and use a different approach than this one. But if it is something that someone in the workshop is interested, we can talk about it, and we can then make we could set you up to use it if it's needed. Essentially, what you do is you use the COPASI on your desktop to set up the simulation you want, and rather than running it, you save it and then you upload it to this website and tell it, okay, run me this on the cloud. So it then sends this to our high performance computing center, runs the tasks, and eventually you get the outcome. So for example, in this example here, we're going to repeat the stochastic simulation 1,000,000 times. Now, that's something you could do on your computer, but the computer will be running for a while. And you might not want, it may be, depending on the model, may be too long, and you don't want your computer tied up. So then you send this to the cloud, and those 1,000,000 simulations get processed in parallel. And so they will run a lot faster than if you just run it in one. Obviously, if you're running only 10, then it's much, much better to run it on your computer, because the time it takes to save the file, upload it, send it to the cloud, wait for the results, download the results, it's much longer than running the 10 stochastic simulations. But if you're running 1,000,000 or 10,000,000, then that's already a different story. So this is also available, and that's kind of my last slide. So I think we still have a little bit of time, which is good, because then we can open up the floor for questions and I can answer them. I may try to answer the questions that are there already. I think there's some that have been answered. But let me try and ask people to open up their mics, and then we can probably talk. Maybe I'll pick the last question, the one about MCA. So, Jirina, do you mind unmuting and asking the question? Maybe you can explain a little more better what is the problem you have in your MCA, that you have infinity values?
Yes, actually, I built a model, but after running it to steady state, I still found many infinitive values in
Oh,
MCA. Under
yes.
the scaled version, but not in the unscaled version. I was getting numerical values under the unscaled version, but when I change it to scaled, it's showing me
Yeah.
infinities.
So those MCA values are things of this form. So they're a special case, but they're a derivative of a function of a variable divided by the change in the parameter. So what COPASI does is that it makes a small change in the parameter and measures the change in that. Now, if one of these, if the p is very close to 0, or if even j is very close to 0, if p is very close to 0, you basically, because in the scaled version, we divide this, we take away the scale, right? So we do the relative change. So relative change is dj divided by j, and dp divided by p. But if p is very close to 0, or if this change here is very close to 0, then you can get an infinity, basically, because of a division by 0. I would think that most likely they're showing infinity because you are in equilibrium state rather than a finite steady state. So if I were you, I would run COPASI for the steady state with the same conditions and check whether it says it's an equilibrium, because it probably has. If it's in equilibrium, then these parameters are not defined because there's no changes. You cannot scale by 0, essentially. And that's where you then would get those values. If you're in one of the projects, if you're staying on, then we could actually have a look more specifically in your case and try to find out an answer.
Yeah, she
Oh,
is in
yes,
one of the projects.
thank you.
Yeah, okay, so we can work that out more on the one-on-one. The other question was
Thank you.
about parameter estimation for electrophysiological models. Yes, we could provide examples. It certainly can be done in the literature. It can be done with COPASI. I guess Stefan pointed out some models. But yes, we could do that. Now, electrophysiological models are a little tricky sometimes for parameter estimation because they essentially have very excitable parts, right? So depending on how the data was obtained, it may or may not be easy to do the parameter estimation, but in principle, yes, that's possible. Again, if you are on one of the project, if you have a project and you're staying for the hands-on sessions, then we can certainly look at this. I have some examples in my presentation tomorrow that are from electrophysiology, so that could be also something we could mention. Yeah.
Yeah, it can be discussed in the project session.
Okay, so in any other questions? Stop sharing.